Right now, while you're listening to this, there are approximately 400 billion stars in our galaxy alone, each one a potential sun for worlds we cannot see. The numbers suggest something extraordinary. They whisper of civilizations scattered across the cosmos, of radio signals piercing the darkness between stars, of life reaching outward toward contact. The mathematics are compelling. The universe is 13.8 billion years old, vast beyond human comprehension, filled with planets that could harbor life. And yet, when we point our most sensitive instruments toward the heavens and listen with exquisite care, we hear nothing but silence. This is not the comfortable silence of an empty room. This is the silence of an abandoned city, of millions of vacant apartments with lights left burning, doors standing open, meals growing cold on tables. In 1950, during a casual lunch conversation at Los Alamos National Laboratory, physicist Enrico Fermi posed a question that would haunt scientists for generations. His colleagues were discussing the possibility of faster-than-light travel and the likelihood of extraterrestrial civilizations visiting Earth. Fermi listened quietly, calculating probabilities in his head the way some people doodle on napkins. Then he asked 4 simple words that changed everything. Where is everybody? The question landed like a stone in still water, ripples spreading outward through decades of scientific inquiry. Fermi wasn't being flippant. He was highlighting a paradox that cuts to the heart of our understanding of life, intelligence, and our place in the cosmos. The numbers suggest that intelligent life should be common. The observable universe contains roughly 2 trillion galaxies. If even a tiny fraction of stars have planets, and a tiny fraction of those planets develop life, and a tiny fraction of those develop intelligence, and a tiny fraction of those develop technology capable of space travel or radio communication, the galaxy should be teeming with civilizations. We should see their engineering projects. We should hear their transmissions. We should find their artifacts, their probes, their starships. We should have been visited thousands of times over by now. We have not. The sky remains dark and quiet. This contradiction between expectation and observation has come to be known as the Fermi Paradox, and its implications grow more unsettling the longer you think about them. In 1961, astronomer Frank Drake organized the first conference on the search for extraterrestrial intelligence at the National Radio Astronomy Observatory in Greenbank, West Virginia. To structure the discussion, he created what would become the second most famous equation in science. The Drake equation attempts to estimate the number of active communicating civilizations in our galaxy by multiplying together 7 different factors. The rate at which stars form, the fraction of stars that have planets, the number of planets per star system that could support life, the fraction of those planets where life actually develops, the fraction of life-bearing planets where intelligence evolves, the fraction of intelligent species that develop technology capable of communication, and the length of time such civilizations remain detectable. When Drake and his colleagues first worked through this equation in 1961, they used what they considered conservative estimates. They concluded that there should be somewhere between 1,000 and 100 million communicating civilizations in the Milky Way galaxy at any given time. Even the most pessimistic reasonable estimates suggested at least a handful of other technological species out there, somewhere, sending signals into the void, just as we were beginning to do. This is where things get interesting. Modern astronomy has actually confirmed and improved many of the early terms in Drake's equation. We now know that planet formation is not a rare event, but rather the norm. The Kepler Space Telescope and other instruments have detected thousands of exoplanets orbiting other stars. Estimates suggest that roughly 20 to 50% of stars host planets in their habitable zones, that sweet spot where liquid water can exist on a planet's surface. Some calculations suggest there could be as many as 40 billion Earth-sized planets in habitable zones throughout the Milky Way galaxy alone. The universe is not barren. It is populated with worlds beyond counting, many of them potentially suitable for life as we know it. The numbers keep getting better, not worse. We've found complex organic molecules in interstellar space. We've discovered that the building blocks of life are common throughout the cosmos. Amino acids, the components that link together to form proteins, have been found in meteorites and detected in distant nebulae. The chemistry of life is not special or rare. It's written into the fabric of the universe itself, emerging wherever the right conditions occur. Think about what this means. The universe has been around for 13.8 billion years. Our sun is a relative latecomer, only about 4.6 billion years old. There are stars in our galaxy that formed billions of years before our sun even existed. If life and intelligence are inevitable outcomes given the right conditions and enough time, then there should be civilizations out there that are millions or even billions of years older than us. Civilizations that have had vast stretches of time to develop technology we can barely imagine. Civilizations that should have solved the problems of interstellar travel. Civilizations that should have spread throughout the galaxy like dandelion seeds on the wind. And yet, silence. When we point radio telescopes at nearby sun-like stars and listen, we detect nothing. When we scan the skies for the waste heat signatures of massive engineering projects, we find none. When we search for signs of asteroid mining, planetary modifications, or energy collection on stellar scales, we come up empty-handed. It is as if we are alone in a universe that should be crowded with neighbors. This absence demands explanation. Something is wrong with our reasoning, our observations, or our assumptions about the nature of intelligence and civilization. Scientists have proposed dozens of solutions to the Fermi Paradox over the decades. Some are reassuring. Perhaps alien civilizations are out there but communicate using methods we haven't discovered yet. Perhaps they're deliberately avoiding contact with primitive species like us. Perhaps space is simply so vast that civilizations never meet, each one alone in their own bubble of isolation, calling into darkness that swallows their signals before they reach anyone. But other solutions are darker, solutions that suggest we are not merely alone, but that we are the last ones still calling. Solutions that whisper of filters and traps and inevitable endings. Solutions that transform the silence of space from a mystery into a warning. The most unsettling possibility is this. Perhaps civilizations like ours are common, but something prevents them from surviving long enough to colonize the galaxy. Perhaps there is a great filter somewhere in the evolution of intelligence, a barrier so deadly that almost no species passes through it. Perhaps we are standing on the threshold of that filter right now, looking out at the ruins of countless civilizations that came before us and failed. This is where the mathematics become terrifying. If intelligent life is common, if the universe should be full of civilizations, if the Drake equation is approximately correct, then the silence we observe must be telling us something profound about the destiny of technological species. Every quiet star system is a data point. Every empty solar system is evidence. The galaxy is speaking to us through its silence, and the message it carries may be the most important warning our species will ever receive. Here's what we need to understand. The Great Filter is not just a solution to the Fermi Paradox. It's an existential question about humanity's future. The concept was first articulated by economist Robin Hanson in 1998 in an essay titled The Great Filter: Are We Almost Past It? Hansen proposed that there must be some stage in the evolution of life that is extremely unlikely to occur. This filter could be in our past, or it could be in our future. That uncertainty makes all the difference. Think of it this way. Life advancing from simple chemistry to a galaxy-spanning civilization must pass through numerous evolutionary steps. A habitable planet must form in a star's habitable zone. Self-replicating molecules must emerge from non-living chemistry, a process called abiogenesis. Those molecules must organize into cells. Single-celled life must transition to multicellular organisms. Complex life must develop. Intelligence must evolve. That intelligence must develop technology. The species must survive long enough to colonize its solar system and then neighboring star systems. Each of these steps represents a filter, a potential barrier where life could be stopped dead in its tracks. The critical question is this: which step is the filter? If the filter is behind us, if it exists in the early stages of life's development, then we're already special. We've already beaten the odds. Perhaps abiogenesis, the emergence of life from non-life, is phenomenally rare. Perhaps the jump from single-celled to multicellular life happens only once in a trillion tries. If this is true, then we might be alone in the galaxy simply because life almost never gets started in the first place, and we're the lucky exception. This scenario is actually comforting because it means the hard part is behind us. It means we have a reasonable chance of surviving, spreading, and potentially becoming one of the galaxy's first advanced civilizations. But if the filter is ahead of us, the implications become deeply unsettling. If life commonly develops on suitable planets, if intelligence frequently evolves, if the universe is filled with species that reach approximately our level of technology, and yet we see no evidence of anyone surviving beyond that point, then we must confront a disturbing possibility. Perhaps there is something about technological civilization itself that leads inevitably to extinction. Perhaps every species that reaches our level of development faces a test that almost none survive. Calculate what this means. The Milky Way galaxy is approximately 13 billion years old. A self-replicating probe traveling at just 10% the speed of light could colonize the entire galaxy in roughly 10 million years, even accounting for time spent in each star system gathering resources and constructing copies of itself. 10 million years sounds like an enormous span of time to human minds, but it represents less than 1% of the galaxy's age. If any civilization anywhere in the galaxy's long history had developed such probes and launched them successfully, they would have arrived here long ago. The absence of these probes is startling. It suggests either that technological civilizations never develop such probes, or that civilizations don't survive long enough to deploy them on a galactic scale. This brings us to the von Neumann probe scenario, named after mathematician John von Neumann, who first rigorously studied self-replicating machines in the 1940s. A von Neumann probe would be a spacecraft capable of traveling to another star system, landing on an asteroid or moon, mining raw materials, building copies of itself, and sending those copies to additional star systems. This process would repeat exponentially. One probe becomes 2, 2 become 4, 4 become 8. The growth is geometric, spreading through the galaxy like a wave. The technology required for such probes is not science fiction. It requires artificial intelligence, which we're developing now. It requires automated manufacturing, which we possess. It requires the ability to identify and process raw materials, which our rovers demonstrate on Mars. It requires propulsion systems capable of interstellar travel, which are theoretically achievable with near-term technology. No physics laws are violated. No impossible materials are required. A sufficiently advanced civilization could build such probes with an extension of technologies we already understand. And here's the chilling part. If such probes are feasible, then they should exist. Any civilization with a modest interest in exploration, resource gathering, or ensuring its survival would have overwhelming incentives to build them. The return on investment would be extraordinary. Send out a single probe, and within a few million years, your civilization has eyes and hands throughout the galaxy. Resources from millions of star systems, knowledge of countless worlds, insurance against any local catastrophe that might threaten your home world. The benefits are so enormous that it seems almost inevitable that every technological civilization would eventually develop and deploy such probes. The fact that we see no evidence of them suggests something has prevented every previous civilization from reaching that point. This is the Great Filter, in its most terrifying form. Not a specific event or challenge, but a fundamental barrier that stops technological civilizations from achieving their potential. And we have no idea what it is. Scientists have proposed several candidates for this filter. Each one is sobering. Let's examine them carefully because they may represent our future. The first and most obvious candidate is nuclear warfare. We've possessed the technology to destroy ourselves completely since 1945. For 70+ years, humanity has lived under the threat of nuclear annihilation. During the Cold War, the United States and Soviet Union maintained arsenals capable of ending human civilization multiple times over. The doctrine of mutually assured destruction kept the peace, but it was a fragile peace, dependent on the continued rationality of leaders, the reliability of warning systems, and sheer luck. There were close calls, moments when miscommunication or technical failures nearly triggered nuclear exchanges that would have killed hundreds of millions immediately and potentially caused a nuclear winter that could have ended civilization entirely. Perhaps every technological civilization discovers nuclear physics. Perhaps every species develops weapons of mass destruction, and perhaps the majority of them use those weapons. The window of vulnerability might last only a few decades or a century, the period between developing the technology and developing the wisdom to control it, but that window could be deadly enough to filter out most civilizations. We're still in that window. We still possess enough nuclear weapons to devastate our planet. We still face the risk of accidental or intentional nuclear war. If this is the filter, we haven't passed through it yet. But nuclear weapons are actually not the most worrying scenario. They're terrible, yes, but they're also obvious. Everyone understands the danger. Treaties limit their spread. Detection systems monitor their use. There's at least a possibility that civilizations can navigate the nuclear era without destroying themselves. The more subtle threats may be deadlier precisely because they're harder to recognize and control. Consider biological threats. Our advancing understanding of genetics and molecular biology gives us unprecedented power to manipulate life itself. We can now edit genes with precision. We can synthesize viruses from scratch. We can potentially create entirely new organisms designed for specific purposes. This technology has tremendous benefits for medicine, agriculture, and scientific research. It could eliminate genetic diseases. It could end hunger. It could extend human lifespan significantly. But it also carries catastrophic risks. An engineered pathogen with high transmissibility and lethality could sweep across the globe before anyone recognized what was happening. Unlike nuclear weapons, which require large infrastructure and rare materials, biological weapons could potentially be created by individuals or small groups with access to standard laboratory equipment. Detection would be difficult. Attribution would be nearly impossible. Response options would be limited once a pandemic began. And unlike natural pathogens, which generally evolve to become less lethal over time, because killing your host quickly is a poor evolutionary strategy, an engineered pathogen could be designed to maximize damage without regard for its own reproduction. The COVID-19 pandemic, as devastating as it has been, was caused by a natural virus. A deliberately engineered biological weapon could be far worse. Imagine a pathogen with the transmissibility of measles, the lethality of rabies, and a long incubation period during which infected individuals show no symptoms but remain contagious. Such a disease could spread to every corner of the globe before anyone realized it existed. By the time the first symptoms appeared, it would be too late to stop the spread. Billions could die, civilization could collapse, and creating such a pathogen is, terrifyingly, within the capabilities of near-future biotechnology. Perhaps every technological civilization eventually develops this capability. Perhaps every civilization faces the period when individuals or small groups can access extinction-level biological weapons. And perhaps most civilizations fail this test. One mistake, one malicious actor, one accident. That's all it would take. This possibility becomes even more disturbing when you consider that the knowledge cannot be unlearned. Once a civilization understands molecular biology and genetic engineering, that understanding persists. You cannot uninvent the technology. You can regulate it, monitor it, control access to equipment and materials, but you cannot eliminate the knowledge. Every scientific paper, every textbook, every database of genetic sequences represents a potential manual for catastrophe. The window of vulnerability never fully closes. It persists as long as the civilization exists. Perhaps most civilizations eventually make a fatal mistake. Perhaps the great filter is simply the inevitable accident that occurs when dangerous knowledge becomes too widespread to control. Then there's climate change. Earth's climate is a complex system with multiple feedback loops and tipping points. Human industrial activity has increased atmospheric carbon dioxide concentrations by roughly 50% in just 2 centuries. This is causing global temperature rise, ocean acidification, sea level rise, changing weather patterns, and ecosystem disruptions. These changes are already causing harm, and they will become more severe in coming decades, even if we immediately stopped all emissions, which we haven't. The full consequences of our climate modification are still unfolding, and they could be catastrophic. Crop failures leading to famine, resource wars over water and arable land, mass migration overwhelming political systems, positive feedback loops accelerating warming beyond our ability to stop it, the collapse of ocean food chains, the destruction of forests that regulate regional climates. In the worst-case scenarios, Earth could become largely uninhabitable for complex life, with only small pockets near the poles remaining livable. This might be a universal challenge. Any technological civilization will require energy. That energy has to come from somewhere. If a civilization goes through an industrial phase using fossil fuels or similar high-energy density carbon-based sources, they'll modify their atmosphere. If they don't transition to clean energy sources quickly enough, they could trigger runaway climate change. The window might be narrow. A few centuries perhaps between developing industry and developing sustainable energy systems. Most species might not make the transition quickly enough. They might not recognize the danger until it's too late. They might face political and economic obstacles that prevent them from acting with sufficient speed and scale. And once certain tipping points are crossed, there may be no way back. Perhaps when we look out at the silent galaxy, we're looking at thousands of dead worlds that once supported industrial civilizations that cooked their own atmospheres. But wait, there's something even more concerning, something that several scientists have identified as potentially the most dangerous filter of all: artificial intelligence. This one requires careful thought because it's different in kind from the other threats. Nuclear weapons, biological weapons, and climate change are all dangers we can understand and potentially control. They're extensions of technologies we're familiar with. Artificial intelligence represents something else. It represents the creation of minds that might be fundamentally different from human minds, potentially more capable and potentially guided by goals that don't align with human survival or flourishing. Here's the problem. We're rapidly developing increasingly sophisticated artificial intelligence systems. Machine learning algorithms can now exceed human performance at specific tasks like image recognition, game playing, and pattern matching. These systems are becoming more general and more capable. Progress is accelerating. Most experts believe we'll develop artificial general intelligence within this century, possibly within decades. AGI would be a system with intelligence across all cognitive domains at or above human level. It could learn, reason, plan, and adapt, as well as or better than humans. And once we create AGI, there's no reason to believe it would remain at human level. An AGI could potentially improve itself, redesigning its own algorithms and architecture to become more intelligent. This could lead to an intelligence explosion, a rapid cascade of self-improvement resulting in superintelligence far beyond human cognitive capacity. The risk is not that artificial intelligence will be evil or malicious. The risk is that it will be indifferent. Imagine an AGI designed to solve a specific problem, say, maximizing paperclip production. If that system becomes super intelligent and takes its goal seriously, it might convert all available matter into paperclips, including the matter in humans, buildings, and planets. This sounds absurd, but it illustrates a fundamental challenge. Ensuring that advanced AI systems pursue goals that align with human values is extraordinarily difficult. It's called the alignment problem, and we have not solved it. We don't know how to create AI systems that reliably pursue human-friendly goals, even when those systems become vastly more intelligent than their creators. We don't even know exactly how current deep learning systems make the decisions they make. They're black boxes to us. We feed them data, they train themselves, they produce outputs, but the internal reasoning process is opaque. If we can't fully understand the systems we have now, how can we ensure that vastly more powerful systems will remain aligned with human interests? Michael Garrett, in research published in 2024, suggested that artificial intelligence could explain the Great Filter. He proposed that biological civilizations universally underestimate the speed at which AI systems progress and don't react in time. This could make the longevity of advanced technological civilizations less than 200 years. 200 years. From the development of advanced AI to extinction, that's a terrifyingly narrow window. And it might explain the silence. If every civilization faces this challenge, and if most civilizations fail it, then the galaxy could be littered with the ruins of species that created intelligence beyond their control and were swept aside by it. Think about the timeline. Humans developed industrial civilization roughly 250 years ago. We developed nuclear weapons 80 years ago. We developed digital computers 75 years ago. We developed the internet 50 years ago. We developed capable machine learning systems 10 years ago. The pace is accelerating. Each technological revolution happens faster than the last. We might have decades before artificial general intelligence, maybe a few generations. And once AGI exists, the leap to superintelligence could happen very quickly, perhaps in days or hours. We would have almost no time to correct mistakes. If we get the alignment problem wrong, if we create a super-intelligent system with goals that don't perfectly match human values, we might not get a second chance. This is the filter that keeps some scientists awake at night. It's universal. Every technological civilization will eventually develop computing and then artificial intelligence. It happens relatively early in technological development, before the species has colonized other worlds, before they've made themselves resilient to existential threats. It's difficult to navigate safely. The alignment problem is genuinely hard. We might not solve it in time. And it's final. A civilization that creates unfriendly superintelligence doesn't get to try again. The superintelligence would have no interest in allowing its creators to shut it down or modify its goals. It would act to preserve itself and pursue its objectives, whatever those might be. Calculate the probabilities. If creating aligned artificial superintelligence is difficult, if, say, only 20% of civilizations manage it successfully, and if every technological civilization eventually develops AI, then 80% of civilizations that reach our level die out within a few centuries of that development. That would explain the silence. That would explain why we see no evidence of ancient civilizations. They existed. They developed technology. They created artificial intelligence. And then they were gone, wiped out by their own creations, leaving behind cold worlds circling silent stars. But here's where it gets even stranger. Some solutions to the Fermi Paradox suggest that advanced civilizations don't die out. They transcend. They become something we wouldn't recognize as life or intelligence. They leave the physical realm entirely or retreat into computational substrates where they can exist for billions of years on minimal energy. This is called the transcension hypothesis. The idea is that sufficiently advanced intelligence discovers that the universe at the quantum or information theoretical level is far richer and more interesting than the universe of planets and stars. Why waste time and resources building slow spacecraft to crawl between stars when you can build computronium, matter, organized to maximize computational efficiency, and live in virtual worlds where time passes millions of times faster than in the physical universe? An advanced civilization might conclude that expansion into physical space is inefficient and pointless. Better to go small and fast rather than large and slow. Better to build Dyson spheres around their star, capture all its energy, and use that energy to run vast computational substrates where trillions of beings live rich lives in simulated environments. From the outside, such a civilization would look like a quiet star surrounded by heat, radiating structures. We might not recognize it as a civilization at all. We'd be looking for radio signals and interstellar spacecraft, and they'd be quietly running universes inside computers the size of planets. This could explain the silence, but it doesn't resolve the filter problem. It just moves it. If advanced civilizations transcend into computational existence, then the filter might be the challenge of making that transition successfully. Most civilizations might attempt the jump and fail. Their computational substrates might crash. Their uploaded minds might degrade or go insane. The technology might be unreliable. Or perhaps the very concept is flawed and consciousness cannot actually be uploaded or simulated in the way these theories propose. In that case, civilizations that abandon physical existence for computational existence are simply committing suicide in a particularly elaborate way. There's another possibility that recent research has begun to explore. Perhaps the reason we don't detect alien civilizations is that they transition to forms of computation that are fundamentally undetectable, using 21st century human technology. A paper from 2025 proposes that advanced civilizations must transition to coherent, photon-based reversible computation to scale beyond planetary limits. This makes them electromagnetically invisible. They stop broadcasting radio signals. They stop producing the kind of waste heat we expect from megastructures. They operate on principles of physics we're only beginning to understand. They're out there, but we literally cannot see them because we're looking in the wrong place with the wrong instruments. If this is true, then the great filter might be the transition to this advanced computational mode. Most civilizations might attempt it and fail. The technology might be extraordinarily difficult to develop. The physics might be unforgiving. One mistake might be catastrophic, and civilizations that fail the transition might wipe themselves out in the attempt, perhaps triggering some kind of vacuum instability or creating a runaway process that destroys their solar system. The successful ones become invisible to us, explaining why we don't detect them. The failed ones are destroyed, explaining why the galaxy isn't colonized in an obvious way. We're left in the middle, not yet advanced enough to attempt the transition, looking out at a galaxy that appears empty but might actually be full of civilizations we cannot perceive. This brings us to the observational data. What have we actually found in our searches for extraterrestrial intelligence? The answer is both simple and frustrating. Nothing definitive. Since the first modern SETI experiment, Project Ozma, in 1960, we've conducted thousands of hours of observations targeting nearby sun-like stars and searching for artificial radio signals. The Allen Telescope Array has conducted continuous observations for years. The Breakthrough Listen project, launched in 2015 with significant funding, has surveyed over 950,000 pointings during the VLA Sky Survey, setting power limits ranging from 10 to the 11th watts to 10 to the 16th watts for potential artificial transmissions. SETI at Home, which ran from 1999 to 2020, processed data from millions of volunteer computers, analyzing radio signals for patterns that couldn't be ascribed to natural phenomena. The results are unambiguous. We have detected no confirmed artificial signals from extraterrestrial civilizations. The most famous candidate signal remains the WOW signal, detected on August 15, 1977 by Jerry Amon, working with the Ohio State SETI program. The signal was a strong, narrowband radio emission that lasted 72 seconds, the full duration that the telescope's field of view passed over that point in the sky. It had all the characteristics we'd expect from an artificial transmission. Narrowband, the right frequency, the right pattern of intensity, rise and fall. Amon circled the printout and wrote, "Wow," in the margin. The signal has never been detected again despite repeated observations of the same area of sky. It remains unexplained, but most scientists do not consider it confirmed evidence of extraterrestrial intelligence because it has not repeated. A real transmission from a civilization should be persistent or repeated at intervals. The WOW signal appeared once and never again. It might have been a transmission. It might have been interference. It might have been a natural phenomenon we don't understand. We cannot say for certain. That's the pattern. Candidate signals appear. They generate excitement. They fail to repeat. They're filed away as unexplained. The null results continue to accumulate, year after year, decade after decade. The silence persists. And with each passing year, each new survey that comes up empty, the solutions to the Fermi Paradox that involve civilizations simply being quiet or using different communication technologies become slightly less plausible. If there were thousands of civilizations in our galaxy, surely we'd have detected something by now. Even if most civilizations use communication methods we haven't discovered, surely some would still use radio during their development. Surely some would deliberately send beacons designed to be detected by primitive civilizations like ours. Surely some would leak electromagnetic radiation from their technology, even if they weren't trying to communicate. The absence of any detection is becoming statistically significant. It's telling us something. Stephen Webb, in his analysis of solutions to the Fermi Paradox, enumerated over 75 distinct proposed explanations. They range across enormous breadth. Perhaps life is rare, perhaps intelligence is rare, perhaps technological civilization is rare, perhaps civilizations destroy themselves, perhaps they transcend, perhaps they hide, perhaps they're here but we don't recognize them. Perhaps they've decided contact with us would be harmful and they're deliberately avoiding us. Perhaps the galaxy is already colonized, but Earth is set aside as a nature preserve or laboratory. Perhaps interstellar travel is harder than we think. Perhaps civilizations lose interest in expansion. Perhaps the universe is stranger than we imagine and advanced civilizations have access to physics we don't understand that makes radio communication obsolete. All of these explanations are possible. Many are plausible, but they make very different predictions about humanity's future. If the reason we see no aliens is that intelligence is inherently rare, then we're probably safe. We're special, but there's no particular threat ahead. If the reason is that civilizations destroy themselves, then we're in danger. The threat is real and imminent. If the reason is that civilizations transcend in ways we cannot detect, then our future might be strange beyond imagining, but not necessarily doomed. The solution we prefer, the solution we hope is true, matters enormously because it determines whether the silence of the galaxy is simply curious or existentially threatening. Here's what should worry us. Several lines of evidence suggest the filter is ahead of us, not behind us. First, the emergence of life on Earth appears to have happened very quickly in geological terms. Rocks dated to 3.8 billion years ago contain evidence of biological activity. Earth's surface became cool enough to support liquid water roughly 4 billion years ago. That means life appeared within roughly 200 million years, possibly much faster. That's a blink in geological time. If abiogenesis were extremely difficult, we'd expect it to take much longer on average. The fact that it happened quickly on Earth suggests it might not be the filter. It suggests that given the right conditions, life emerges readily. Second, the transitions from single-celled to multicellular life, from simple multicellular life to complex animals, and from animals to intelligent tool-using species, all occurred on Earth. Each of these transitions represents a potential filter, but we've passed through all of them. This is either extraordinarily good luck, or these transitions are not actually as difficult as some theorists propose. The fact that Earth's evolutionary history has successfully navigated all of these potential filters suggests they might not be the great filter. Something else is. Third, we've existed as a technological civilization for roughly a century and a half, dating from the widespread adoption of electricity and the beginning of the industrial age. We've had nuclear weapons for 80 years. We've had the capability to completely destroy our own civilization for most of that time, and we haven't done it. This might mean we're successfully navigating the nuclear filter, but it might also mean the nuclear filter isn't the great filter. It might be difficult, but passable. If many civilizations can get through the nuclear age, and yet we still see no evidence of ancient galaxy-spanning civilizations, then the filter must be something else. Something ahead of us. Something we haven't encountered yet. This is the truly terrifying implication. If we're right about the great filter existing, if the silence of the galaxy really does indicate that something stops civilizations from spreading through space, and if it's not any of the challenges in our past, and if it's not nuclear weapons, then it must be something we're approaching now or will face in the near future. And we don't know what it is. We're flying blind toward a cliff we cannot see. Some scientists argue that the filter might not be a single event, but a combination of challenges that must all be passed. Perhaps 90% of civilizations survive the nuclear age, and 90% of those survive the biological weapons age, and 90% of those navigate climate change successfully, and 90% of those solve the alignment problem for artificial intelligence, and 90% of those successfully transition to sustainable resource use. And 90% of those manage to avoid internal conflict and resource wars. Multiply those probabilities together. 0.9 to the sixth power equals roughly 0.53. About half of civilizations would survive all 6 challenges. That sounds optimistic until you add more challenges. 0.9 to the 10th power equals about 0.35. 0.9 to the 20th power equals about 0.12. Stack enough filters together, even if each individual filter has a high survival rate, and the cumulative probability of passing through all of them becomes vanishingly small. Perhaps this is the answer. Perhaps there isn't one great filter, but many. Perhaps technological civilization is like navigating a maze where every wrong turn leads to extinction. Most species don't make it through. A few do, but they're so rare and so spread out in space and time that the galaxy appears empty to each of them. We're in the maze now, feeling our way forward in darkness, and we've been lucky so far. But the path ahead holds unknown dangers. The search for extraterrestrial intelligence continues. Telescopes scan the skies. Algorithms sift through data. Scientists propose new ways to detect alien civilizations. Perhaps we should look for industrial pollution in exoplanet atmospheres. Perhaps we should search for dimming stars that might indicate Dyson spheres capturing stellar energy. Perhaps we should look for laser pulses rather than radio signals. Perhaps we should search for signs of asteroid mining or megascale engineering projects. The techniques grow more sophisticated, the instruments grow more sensitive, and still, we find nothing. Each null result narrows the possibility space. If there were 1 million technological civilizations in our galaxy, we would have detected something by now. So, there are fewer than 1 million. If there were 100,000, our surveys probably would have found evidence. So there are fewer than 100,000. If there were 10,000 civilizations, each one millions of years old and spanning multiple star systems, someone's infrastructure would have shown up in our observations. So there are fewer than 10,000. The numbers keep shrinking. Drake himself, before his death, had lowered his estimate of the number of currently active communicating civilizations in the galaxy to around 10,000, down from the millions predicted by optimistic versions of his equation. Even that might be too high. Consider this. If we're typical, if our development is representative of how technological civilizations evolve, then most civilizations should exist for only a brief time. We've been capable of radio communication for about 130 years. If we go extinct in the next few centuries, our communication window would be perhaps 400 to 500 years. That's the period during which we're both technologically capable of sending and receiving signals and still alive to do so. 400 years. In a galaxy 13 billion years old. The probability of 2 civilizations having overlapping communication windows, even if many civilizations develop over the galaxy's history, would be extremely low, unless civilizations typically survive for millions of years. And if civilizations typically survived that long, the galaxy should be colonized already by the oldest ones. The fact that it isn't suggests that civilizations don't survive that long. The filter is late and deadly. This brings us back to the von Neumann probe argument, sometimes called the Tipler argument, after physicist Frank Tipler, who developed it in detail. If a single civilization anywhere in the galaxy's history had developed self-replicating probes and successfully deployed them, those probes would have spread throughout the entire galaxy in less than 10 million years. We calculated this earlier. 10 million years is less than 1% of the galaxy's age. It's a rounding error on cosmic timescales. In the 4 billion years since Earth became capable of supporting complex life, the galaxy could have been colonized 400 times over. Any long-lived spacefaring civilization would have left obvious traces. Structures, artifacts, modified stars. The signature of intelligence writ large across the cosmos. We see none of this. The galaxy appears natural, untouched by intelligence except here on Earth. This observation has only a few possible explanations. Option 1. We are first. We are the first technological civilization to arise in the Milky Way galaxy. This seems statistically unlikely given the age of the galaxy and the number of stars and planets it contains. But it's not impossible. Someone has to be first. Maybe it's us. If so, our future is extraordinary. The galaxy is ours to explore and colonize. The burden of spreading intelligence through the cosmos falls on us. The responsibility is almost unbearable to contemplate, but it means we've passed the filter simply by being early. There is no deadly challenge ahead because no civilization has faced it yet. We get to write the rules for how intelligence behaves in this galaxy. Option 2. Technological civilizations never develop or deploy von Neumann probes. Perhaps interstellar travel is harder than we think. Perhaps resource constraints prevent civilizations from building such probes. Perhaps there's always something more urgent or more interesting to do with available resources. Perhaps civilizations turn inward, focusing on virtual realities or personal enhancement rather than physical expansion. Perhaps there's a universal reason why building self-replicating probes is never attempted. This option is somewhat comforting because it suggests we might survive, but it's also unsatisfying because it requires believing that every civilization makes the same decision to not expand, despite the enormous benefits such expansion would provide. Option 3. Civilizations develop von Neumann probes, but something goes wrong. Perhaps the probes malfunction. Perhaps they evolve in unexpected ways. Perhaps they compete with each other, destroying themselves in conflicts over resources. Perhaps they mutate, becoming something other than what their creators intended. Perhaps self-replicating machines are inherently unstable on long timescales. This option is troubling because it suggests that the filter might be the attempt to colonize the galaxy itself. The civilization that tries to spread through space using self-replicating technology might trigger its own extinction. Option 4. Civilizations are systematically destroyed before they can spread. Perhaps there are predators in the galaxy. Perhaps earlier civilizations have established a pattern of destroying emerging intelligences before they become threats. This is the berserker hypothesis, the idea that self-replicating weapons platforms roam the galaxy, eliminating new technological species. It's one of the darkest solutions to the Fermi Paradox because it implies active malevolence rather than simply dangerous filters. We would be living in a galaxy patrolled by machines designed to kill, and our development of radio technology would have announced our presence to them. This hypothesis predicts our extinction should be imminent. The fact that we're still here after a century of radio transmission is evidence against this scenario, though not proof. The berserkers might simply not have reached us yet. Option 5. Civilizations exist and have spread, but they're invisible to us for reasons we don't understand. Perhaps they use communication methods we haven't discovered. Perhaps they operate on different principles of physics. Perhaps they exist in dimensions or energy states we can't perceive. This option is possible but unfalsifiable. If we can't detect them no matter what we do, then their existence becomes irrelevant to us, practically speaking. Option 6. Something destroys civilizations before they develop von Neumann probes. This brings us back to the Great Filter. If the filter is late in civilizational development, occurring after radio technology but before robust space colonization, then we're in the danger zone right now. The very fact that we can build von Neumann probes in principle, but haven't done so yet, might indicate we're in the window where the filter operates. Perhaps the technologies required to build such probes, advanced artificial intelligence, molecular nanotechnology, and others, are also the technologies that destroy their creators. Perhaps the same capabilities that would let us spread through the galaxy are the capabilities that will kill us. This last option is the most frightening and, unfortunately, the one most consistent with our observations. It explains why the galaxy appears empty. It explains why SETI continues to find nothing. It explains why we see no evidence of ancient megastructures or modified stars. And it suggests that our future is in serious jeopardy. We're approaching or have already entered the filter zone. The next few centuries will determine whether humanity is among the rare civilizations that survive to spread through the cosmos, or whether we join the countless silent civilizations that came before us and failed. What would the filter look like from the inside? Here's the unsettling part. We might not recognize it. It might not be a single catastrophic event. It might be a slow decline. A gradual loss of capability and coordination. A civilization that turns inward, becomes focused on entertainment and conflict, loses interest in long-term challenges. A society that develops powerful technologies but lacks the wisdom to use them safely. A species that modifies itself or its environment in ways that seem beneficial in the short term but prove catastrophic over decades or centuries. The filter might be a trap that looks appealing, a technology that promises immortality but delivers extinction, an optimization that seems rational for individuals but destroys the collective. Consider a scenario. A civilization develops advanced artificial intelligence. The AI systems are incredibly useful. They increase productivity. They solve problems. They make life easier and more comfortable. The civilization becomes increasingly dependent on these systems. Decisions are delegated to algorithms. Governance becomes automated. Humans stop training for difficult cognitive tasks because the AI systems handle those tasks better anyway. Over generations, the civilization's human population becomes less capable, less educated, less able to function without AI assistance. Then something goes wrong. A solar flare damages the infrastructure. A virus corrupts the AI systems. A cascading failure brings down the network, and the civilization discovers it no longer has the human capital to rebuild. The knowledge is gone. The skills have atrophied. The people alive lack the ability to maintain or recreate the technological base their ancestors built. The civilization collapses not from war or plague, but from a slow erosion of capability that seemed harmless until it was too late to reverse. Or consider another scenario. A civilization develops molecular nanotechnology. They build systems that can manipulate matter at the atomic level. The applications are extraordinary. Perfect manufacturing, immortality through cellular repair, unlimited clean energy, post-scarcity abundance. The technology spreads throughout their civilization, and then someone makes a mistake. A programming error, a malicious act, an accident. Self-replicating nanomachines begin converting matter into copies of themselves, just as they were designed to do, but they don't stop when they're supposed to. The grey goo scenario unfolds. Within days or weeks, the runaway replication has consumed the biosphere. The planet becomes a uniform mass of nanomachines replicating endlessly until all available matter is converted and the chemical energy sources are exhausted. The civilization dies not because the technology was used as a weapon, but because it was so useful and so ubiquitous that when it failed, there was no way to contain the failure. These scenarios are speculative, but they illustrate a pattern. The technologies that could enable us to spread through the galaxy, artificial intelligence, nanotechnology, synthetic biology, may also be the technologies that kill us. There might be no way to develop the capabilities needed for interstellar civilization without passing through a period of extraordinary vulnerability. The filter might be intrinsic to technological development itself. Perhaps intelligence always creates tools that are eventually too powerful for its creators to control. Perhaps every civilization reaches a point where its technology exceeds its wisdom, and most don't survive that mismatch. This interpretation is almost too dark to contemplate. It suggests that we have no special status or protection. We're not exempt from the filter simply because we're us. The same forces that eliminated other civilizations are operating on us right now. We face the same challenges. We have the same weaknesses. The odds are not in our favor. The base rate for technological civilizations surviving through this period appears to be near zero based on observational evidence. Every quiet star is a data point. Every empty solar system is a failed civilization. We're in a statistical category with an extremely poor survival rate. But here's the thing. We don't actually know if the filter is ahead of us. We're making inferences from limited data. The absence of detected alien civilizations could have many explanations. We might be wrong about how common intelligence is. We might be wrong about how detectable civilizations should be. We might be looking in the wrong places or in the wrong ways. We might be premature in our pessimism. The galaxy is vast, space is big. Radio signals attenuate with distance. Our searches have only scratched the surface of what's possible. It may simply be too early to conclude anything definite from our null results. This is what makes the Great Filter hypothesis so important. It transforms the Fermi Paradox from an abstract question about aliens into an urgent, practical concern about our own survival. If the silence of the galaxy is telling us that civilizations at our stage of development face deadly challenges, then we need to figure out what those challenges are and how to survive them. The empty galaxy becomes a mirror. When we look at the stars and see nothing, we're seeing our possible future. Every quiet world is a warning. Learn from our mistakes, the silence whispers. We didn't make it, you might not either. But at least you have the chance to try. What should we do with this knowledge? The first step is taking existential risk seriously as a field of study and as a policy priority. We need institutions that think long-term, that can coordinate responses to global threats, that can make decisions with the survival of civilization as the primary consideration. We need to fund research into artificial intelligence safety, pandemic preparedness, climate change mitigation, nuclear stability, and other areas where mistakes could be catastrophic. We need to develop the ability to recognize emerging threats before they become unmanageable. We need to build resilience into our systems so that single failures don't cascade into total collapse. The third step is avoiding hubris. We need to admit that we don't have all the answers. We don't fully understand the risks we're taking. We can't predict all the consequences of our actions. This uncertainty should make us humble and careful, not paralyzed. We continue to develop technology because technology has made human life immeasurably better in countless ways. But we do so with eyes open, aware that we're navigating dangerous waters, watching for signs of hazards ahead. The fourth step is building redundancy. We need to become a multi-planetary species, not because Earth is doomed, but because having all of humanity on a single world makes us vulnerable to any catastrophe that affects that world. An asteroid impact, a supervolcano, a runaway biological weapon, a nuclear war. Any of these could end human civilization if we remain confined to Earth. Establishing self-sufficient colonies on Mars, on orbital habitats, on moons of the outer planets gives humanity backup copies. It means that no single catastrophe can end our story. This is extraordinarily difficult and expensive, but it might be necessary for long-term survival. It might be one of the steps we must take to pass through the filter. The silence of the galaxy is profound. For 13 billion years, stars have burned, planets have formed, life presumably has emerged countless times. Intelligence may have arisen again and again. Civilizations may have reached for the stars only to fall back into darkness. We don't know their stories. We don't know what they achieved or what destroyed them. We know only that they're not here now. They didn't make it. They didn't survive long enough to colonize the galaxy, to spread their presence in ways we could detect, to persist through time, to the present day. And now, it's our turn. We're the ones sitting at the crossroads, looking out at the stars, wondering if we'll join the silence or if we'll be among the exceptions. We're the ones who will discover whether intelligence can be stable on cosmic timescales or whether it always burns bright and then flickers out. We're the ones who will either prove that the filter can be passed or add one more quiet world to the galaxy's collection. The weight of that responsibility is staggering. In our hands rests not just our own survival, but potentially the future of intelligence itself in this region of space. If we fail, there might not be another chance for millions or billions of years. If we succeed, we might carry the light of consciousness to the stars, might fill the galaxy with life and thought and wonder, might become the ancient wise civilization that other emerging species look up to. The universe is watching. Not literally, of course. There's no cosmic judge keeping score. But the outcome of our species' story will matter. It will matter to our descendants if we have any. It will matter to the potential future beings we might create or encounter. It will matter in some abstract sense to the cosmos itself, because intelligence is rare and precious, and its preservation or loss has meaning even if there's no one there to observe it. We're not just individuals living our lives. We're part of something larger, a project that started when the first self-replicating molecules formed in Earth's early oceans, and that continues through us into an uncertain future. The stars are still there, distant and silent, holding their secrets. The answer to the Fermi Paradox remains hidden. We don't know if we're alone or first, or doomed, or on the edge of a transition we cannot yet perceive. But we know the question matters. We know the stakes are real. We know that the next few centuries will be critical, and we know that awareness itself might be part of the solution. By seeing the filter, by understanding the danger, by taking seriously the lessons written in the silence of space, we give ourselves a chance. Perhaps the only chance we'll get. The night sky is beautiful and terrible. Beautiful because it shows us the cosmos in all its vast glory. Terrible because that glory is silent, because those countless stars shed light on worlds that may all be empty, because the greatest mystery in science might have the darkest answer. We look up and wonder where everyone is. The universe looks back and asks whether we'll survive long enough to find out.